This video explains the chain rule for differentiating composite functions and proves why it works. The proof is presented intuitively rather than through overly academic methods, making it easy for high school students to understand. The composite function of two functions, gy and fx, can be written as g of x, which is a function of x alone. In this case, the derivative dz dx is equal to the product of the two derivatives dz dy and dy dx. This is called the chain rule of differentiation. Let's take the function x squared plus 3x plus 1 raised to the power of 100 and differentiate it with respect to x. If we tried to differentiate this directly, we'd have to expand the entire expression first, which is practically impossible. But by applying the chain rule, we can solve this quite easily. First, let's set the expression inside the parentheses to y. Now, the entire function becomes y to the power of 100. When we differentiate this with respect to y, we get 100 times y to the 99th power. Next, we differentiate the expression inside the parentheses with respect to x, which gives us 2x plus 3. Now let's apply the chain rule. dz dx is equal to dz dy multiplied by dy dx, which equals 100 times y to the power of 99 multiplied by 2x plus 3. Then, by substituting the original expression in x back for y, we can find the final derivative we're looking for. The derivative we've calculated this way has a value of 300 when x is 0. In other words, the instantaneous rate of change of z with respect to x at 0 is 300. Now, let's look at a second example to see how the chain rule works using simpler functions. Suppose z equals y squared and y equals 2x plus 1. According to the chain rule, dz dx is equal to dz dy multiplied by dy dx. Here, dz dy is 2y and dy dx is 2. Multiplying these gives us 4y. Finally, by substituting 2x plus 1 for y, we get 8x plus 4. We can see that this result is the same as the one obtained by expressing z entirely in terms of x and then differentiating directly with respect to x. Now, let us prove the chain rule. Delta z over delta x is equal to delta z over delta y multiplied by delta y over delta x, provided that delta y is not equal to 0. As delta x becomes infinitely small, delta z over delta x becomes the derivative dz dx. Likewise, delta z over delta y and delta y over delta x become the derivatives dz dy and dy dx respectively. Therefore, dz dx becomes equal to dz dy multiplied by dy dx, which proves the chain rule. However, there is one assumption in this proof. That is, delta y must not be equal to 0. If delta y is equal to 0, then delta z over delta y itself is not defined. In some proofs of the chain rule, the case where delta y equals 0 is included and treated from the very beginning. Although this approach is mathematically rigorous, it is extremely complicated and can feel like a huge barrier for high school students trying to understand it. In this video, instead, the case where delta y equals 0 is treated completely separately, allowing the proof to be presented in a much more intuitive and easy-to-understand way. Now, suppose that delta y is equal to 0. In other words, in the function y equals f of x, y does not change even when x changes. Therefore, y is a constant and can be written as c. In this case, dy dx becomes 0. Also, in the function z equals g of y, if y does not change, then z does not change either. Therefore, no matter how much x changes, the value of z remains a fixed constant. In this case, dz dx becomes 0. Now, let's calculate the product of dz dy and dy dx when delta y is 0. Technically, dz dy is not defined when delta y is 0. However, we can still express it algebraically. Since dy dx is 0, as we saw earlier, the product of dz dy and dy dx becomes 0 algebraically. Therefore, from a purely algebraic standpoint, dz dx is equal to the product of dz dy and dy dx, since both have the value 0. Therefore, even when delta y is 0, the chain rule formula dz dx equals dz dy multiplied by dy dx holds computationally. In conclusion, whether delta y is 0 or not, we can still apply the chain rule as usual. Let's look at an example where delta y is 0. Suppose z equals y squared and y equals 10. In this case, since f of x is a constant function, dy dx is always 0. Expressing z entirely in terms of x, z becomes 100, which is a constant. Therefore, dz dx is always 0. Even when delta y is 0, dz dy still becomes 2y through straightforward algebraic calculation, separate from the formal definition of differentiation. In this case, dz dy multiplied by dy dx becomes 0. Therefore, the chain rule dz dx equals dz dy multiplied by dy dx still holds. The material discussed earlier is from the book The Why of Mathematics. This book provides clear explanations for many formulas and principles that are left unexplained in most math classes and textbooks. Depending on the reader's needs or interests, even reading just a few topics in this book would make it more than worth its price. This book is primarily for high school students and math teachers. The final few chapters of the book cover some fundamental math for science, engineering, economics, and business majors that are often skipped without explanation, making them useful even for early undergraduates. Refer to the description for a brief table of contents. You can order this book online on Amazon.